Hello. Excuse me. Today we're going to look at the basics of electric circuits. We're going to review some of the simple electric circuit rules, and by the end you'll hopefully be able to work out what happens when you plug different things into electric circuits, and how you can change them. So start off, see what you can remember. Can you draw a circuit for me? Hopefully you've got a mini whiteboard in front of you. You've got a mini whiteboard in front of you. Can you draw a circuit that has two bulbs, a ammeter, a voltmeter, a battery of cells, and a resistor? Just give you a minute or two to do that. Pause the video and unpause when you think you have done. Go. Draw that. Do it. Are you done? Right, well, here is my low quality version. Come on. Here we go. We have, now there are different ways you could have drawn this. This is my battery of cells, long line and a short line, long line, short line. If you just have one of them, it's a cell. I'm giving it away. I put a voltmeter over the top here, but you could put a voltmeter here or here. My two bulbs, a circle with a cross in, a resistor, which is a rectangle, and an ammeter, a circle with a in it, capital A in it. Did it look like that? Notice I've drawn these nice relatively straight lines. They're not curved. I've not drawn any components on the corner. Yeah. Okay, so you've just seen some of the components. How many other ones do you remember? So clear your whiteboards off. Use your arm, use your sponge, use anything, as long as it's yours. Can you write the numbers 1 to 13, and then next to 1 to 13, can you write the names of the what these different symbols mean? For example, number 3 you already know is a bulb, because I asked you to do that, and hopefully you can remember the difference between 4 and 5, because you've also done that. So write the numbers 1 to 13, and then write what each of those things are next to it. The number. Go again, pause the video and just do it. Write the number 1 to 13, write the answers, pause the video, unpause when you're done. Okay, hopefully that's enough time. I'm going to show you the answers. Check, give yourself a tick or a cross or whatever, depending on how you have gone. So number 1 is an open switch, and number 2 is a closed switch. They're basically the same thing. Switch is open, circuit's not working. Switch is closed, the circuit is working. Number 3 is a bulb. You see those in your house all the time. 4 is a cell, and 5 is a battery. The difference between a cell and a battery: cell is just one, battery is more than one. A voltmeter is a V in a circle. You knew that already. The rectangle with an arrow going through it is a variable resistor. Any of those rectangles is a kind of resistor. So if you see those, know it's a kind of resistor. So arrow going through it means it's a variable resistor. A little kind of tick going through it means it's a thermistor, a resistor that changes due to temperature, thermal. Number 9, the two little arrows coming in, they're supposed to represent light, so that's a light dependent resistor, also known as an LDR. Number 10 is a plain old resistor, nothing in it. Number 11 is a fuse. Number 12 is an ammeter, so it's an A in a circle. And number 13, which is my drawing, which wasn't the greatest one, is an LED, or a light emitting diode. It's kind of like an arrow with two arrows coming out. Yeah, it's not my greatest drawing, but you didn't come here for the art. Okay, so let's do a definition of what current is, and I'm going to show a little animation of what current is. So if you were going to write a flashcard, the question I put on one side is, what is current? What is current? Oh, and here we go. The definition of current. Current is a measure of the rate of flow of electric charge in a circuit. Basically, how fast do the electric charges move in a circuit? That's what current is. Electric charge is measured in something called coulombs, after Mr. Coulomb, and shorthand for coulombs is just the letter C. Current is measured in amperes, after Mr. Ampere, and it's measured using an ammeter. You could also just say amps. And the definition of 1 amp is when you have 1 coulomb of charge flowing every second. It's a little diagram on the right hand side. An ammeter must be connected in series as it measures the current flowing through. Maybe I'll have a little animation for you. Here we go. So here I have a little electric circuit. I've got my battery. Actually, it's a cell because it's just one. And I've got a bulb. And I've got an ammeter. And the switch is open at the moment. When I close the switch, hopefully you'll see the electrons flowing. You can see these little negative electrons and they're flowing round. And it's got a current of 1 amp. Which means every 1 second, one of these little electrons passes a point. So if you just take here, 1, 2, 3, 4. So every second, one of them is going past. So that, by definition, is 1 amp. That's 1 coulomb, not 1 electron, 1 coulomb of charge. If I open the circuit, they can't flow. Doesn't work. So let's go back to the PowerPoint. So current is a measure of the rate of flow of electric charge in the circuit. Electric charge is measured in coulombs. Current is measured in amps using an ammeter. And 1 amp is 1 coulomb every second. And there is an equation to go with this. Hopefully you've got that. If you need to pause, you can pause to write it down. And this is the equation. Charge is current times time. Now they use the letter Q for charge because C is used for something else. So they can't just do C. So Q is to represent charge. And current, they use the letter I because I think it was a French guy who came up with the term or measured Mr. Ampere. He's French, and he, instead of calling it current, he called it intensity. So it's I, and time is time. So charge is measured in coulombs, current is measured in amps, and time is measured in seconds. So the equation Q equals I T. Another thing to stick on your little flashcard. What is current? What is charge? Go. Little pictures. Exciting. Oh, and those of you who are feeling brave, can you turn that into a little formula triangle? If you were going to turn it into a formula triangle, you could do a Q on the top, and then the I and T would be on the bottom. Okay. Question time. Get your whiteboards out, clean them off. Can you write down the answers to those questions? What device do you use to measure current? What is current measured in? What letter is used to denote current? Current is the flow of what? And what equation do you know that has current in it? Pause. Answer the questions. Pause. Answer the questions. I will give you the answers in a moment. Ready? Boink. What device do you use to measure current? You use an ammeter. What is current measured in? It's measured in amps or amperes. What letter is used to denote current? We use the letter I, because the French gentleman that named it intensity, or probably intensity. Current is the flow of what? It is a flow of charge. Although I suppose you could say electrons if you're feeling cheeky. And what equation do you know that has current in it? For example, Q equals IT. Another one, not finished yet. What is the name? Name the unit of charge and write its symbol. What unit should you use for time? And then can you have a go at using the equation Q equals IT? If you have a current of 0.5 amps, and it flows for A, 20 seconds, and B, 5 minutes, C, 1 hour, work out the charge. Q equals IT. Q equals IT. So do I times T for 20 seconds, 5 minutes, 1 hour. But don't forget, must be in seconds. 20 seconds in seconds. 5 minutes, how do you convert that to seconds? And 1 hour, convert it to seconds. Go. I will wait whilst you work out the answers. Pause if you need more time. Are you ready? Excellent. The unit of charge is coulombs, and we use the letter C. The unit of time is seconds. We use the letter T. And for the first one, we do 0.5 amps times 20 seconds. That gives us 10 coulombs. For the second one, we use 0.5 times, and then we have to convert 5 minutes to seconds. So I did 5 times 60, which is 300, times 0.5 is 150. And 0.5 times 1 hour, which is 60 seconds, 60 minutes, 3,600 times 0.5 gives you 1,800. Well done if you got all of those, and if you didn't, I'm not going to judge. This isn't working, so I have a different one. So here we have a little battery. Here's battery's not a little battery at all, it's massive and it's a cell. And here we have a little simpler version. This animation is really slow and clunky. Basically, you can see... maybe I'll try and refresh it. Not liking it at all. Thanks, Vet. We love you. Ready. You can watch this bit on double speed if you want. I've pretty much broken it. No. Starting up. Oh, it's just as bad. Excellent. I might not show this very well. But basically what I was trying to show is, so the battery here forces these electrons around. The electrons travel around the circuit. But when they're in the circuit, what happens is they bump into atoms. Everything's made of atoms. And when they bump into atoms, it slows them down. So you can see that they're all tightly packed together. Then here, they're like crashing into the atoms that are in the resistor or in the wire. And that slows them down. I'm going to kill that one because it's just so painfully slow. I do have a slightly different version. So here I have a slightly different circuit. I've got one battery. And here I've got 2 ammeters on either side of the bulb and a voltmeter. If I turn the circuit on, I can see that I've got 0.3 amps, 0.3 amps. If I add another cell, so I'm pushing harder on the electrons, look, the current goes up. So I'm pushing harder, and if I add another one, the current goes up even higher. So if I add more batteries to my circuit, if I push the electrons harder, they go faster. That makes sense. It makes total sense. But what if I go the other way? What if I start adding more bulbs? I put more obstacles in the way. Let's turn it on. Oh, look. It was 0.9. Now it's gone to 0.45. The current goes down. The current goes down. So if you put more things in the way, if you make the resistance higher, the current actually slows down. Let's do another bulb. Gosh, this is complicated. If I add more bulbs, the whole resistance of the circuit increases and the current goes down. Oops. Too far. Okay. What is electron flow? What is resistance? Maybe this is another flashcard. Okay, so, just a simple one. Resistance is a measure of how much a material tries to stop electricity passing through it. If you think of electricity as like people going around an assault course, resistance is how hard are the activities, the exercises they have to do on the assault course. Like if it's a really low resistance, it could be just like walking over a plank. If it's a really hard one, it could be that one where you have to do the monkey bars and you go across, and that would be a higher resistance. Resistance is how much it tries to stop or slow down electricity passing through it. Here we have a look at the circuit. I'm gonna. Can I pause it? I can pause it for a second. Okay, so first of all, let's go back to the beginning. First of all, look, it has a low resistance. Low resistance. The battery, 9 volts, doesn't change. Then what happens is I make the resistance go higher. Look what happens, 1, to the current, and 2, to how fast those electrons are moving. 1 amps, those electrons are flying. But then as I increase the resistance, look, the current gets much, much slower. 3 ohms, 3 amps. 3.5, 2.4. 4. Basically, as the resistance goes up, the current goes down. As the resistance goes up, the current goes down. If we go the other way, if the resistance goes down, the current would go up. Like it's getting slower and slower. Every time I increase the resistance, the current gets slower. I can talk slower. Can I get it to stop? Can't remember. It's going slower. 0.15. It's not gonna stop. But let's just move it because I'm bored. Okay, so if you increase the resistance, you reduce the current. In a series circuit, if you increase the resistance, the current will decrease. Another note. Good. Very good at this. I knew what you were going to write. Okay, got it. Splendid. And there is an equation to go with this. To work out the resistance, you do the voltage divided by the current. Here we have R is V over I. Or you could rearrange it, change the subject using the correct terms that maths use. Voltage is current times resistance. V equals I times R. V, volts or voltage, its proper name is potential difference. V, potential difference, measured in volts. I, we know, is current and it's measured in amps. And R is resistance and it's measured in ohms. O-H-M-S. And you have to use this little Greek letter, omega, capital omega, as the symbol. So, shall we have a go using this equation? Oh, first of all, there's a triangle. V equals IR. I know some of you like triangles. Remember, if you want to work out the triangle, you just cover one up. So if I want to know I do V divided by R. If I want to know R, I do V divided by I. If I want to know V, I do I times R. Easy. So, example. A filament bulb has a current of 20 amps and a potential difference of 100 volts. What is the resistance? So, V divided by I equals R. So 100 divided by 20 equals 5 ohms. Easy peasy. Here we have 5 questions. Pause the video and answer the questions. It's all the equation. V equals IR. You might have to change the subject. V equals IR, but you can do it. Answer those questions. 5. I'll give you the answers in a minute. Pause once and unpause once you have finished. We ready for the answers? Splendid. The first one, 230 volts, 10 amps. We do 230 divided by 10 is 23 ohms. The second one, 60 ohms, 12 volt battery. We do 12 volts divided by 60, which is 0.2 amps. Another one, 230 volts, current of 5 amps. So we do 230 divided by 5 is 46 ohms. Troy tractor has 4.5 volts, a resistance of 15 ohms, so we do 4.5 volts divided by 15 is 0.3 amps. And the last one, 6 volts, 4 ohms, so you do 6 divided by 4, 1.5. Boom. Here's a little simple animation of an electric current going in series. Notice those electrons, they're like going in single file and they're going round in a loop, round in a nice little loop like this. Notice no electron, you can't have one electron going faster than the other, because if they would, they'd crash into the next one. And you can't have one going slower, because the one behind would bump into it. So they all have to move at the same rate. They all have to move at the same speed through the circuit, which allows us to have a really handy way of working out what the current is in a series circuit. If you know the current in one place, you know the current everywhere. So if I know the current over here is 1 amp, then the current down here is also 1 amp. And the current up here is 1 amp. Current is exactly the same everywhere in this series circuit, because there's only one place. Now you can, if you add more resistance, the current might go down, but it will go down everywhere. If you add more cells, the current might go up, but it will go up everywhere. What happens in one place happens in all the other ones. So let's have a go. If this is 3 amps, oh, mouse stopped working. If this is 3 amps, what is this? What is this? Hopefully you realise that this is also 3 amps. If this is 11 amps, what is this? What is this? Well, obviously, if this is 11 amps, the other two also have to be 11 amps. We're not supposed to have that. Okay, so I'm just going to jump. Right, so one of these things. The thing isn't working. Switch. Excellent. Now, one of the things you're going to have to do, one of the PAGs that they expect you to know for these exams is the relationship between voltage and current basically, if you change the voltage, how does the current change? Now, for example, this is what the circuit would look like. You can put my bulb in here, you have a voltmeter, and you have an ammeter, and what happens is when you change the variable resistor, this makes the resistance go down. When the resistance goes down, the current goes up. When the resistance goes up, the current goes down, just like that. And so what's happening here is you're changing this, and so you get different values for voltage and current. And you can do it with a bulb, you could do it with a diode, you could do it with a resistor, and you can do it with a wire. Nice and simple.